Welcome to lecture 36. In this lecture, I will be talking about how to solve the U1 path integral. Recall that in lecture 35, we found that the gauge-fixed partition function for a pure U1 gauge field was given by the expression listed in equation 36.1. It's a path integral over the gauge field A and over the ghost field C bar C times the exponential of minus an action that comes in three parts. There's the gauge part, which is FAB squared. There's the gauge fixing part, which comes in with the square of the gauge condition G of A and the arbitrary gauge fixing parameter Xi. And the ghost part, that is C bar C times the derivative of the gauge fixing condition with respect to the gauge fixing parameter. We now want to solve this partition function in the present lecture. To get started, we have to choose a gauge condition or a class of gauge conditions that we want to investigate. All choices for G of A must lead to the same result, but some choices lead to easier calculations for the partition function than others. The canonical choice for relativistic quantum field theory is the Landau gauge. G of A is dA AA. And since the gauge transformation is the gauge field A going to A minus the derivative of the gauge function alpha under gauge transformations, this immediately gives us the explicit form of the ghost action, which is the integral over C bar C times the derivative of G. Since G is the derivative of A, we have one derivative of A and the derivative of the A with respect to the gauge fixing parameter. That gives us minus the alpha that we can bring over to the other C. So we end up with an expression that looks like a kinetic term for the ghost fields C bar and C. The ghost action does not depend on A, and as such, and additionally, the gauge part of the action FAB, and the gauge fixing part of the action, which is dA squared, do not depend on the ghost fields. This is nice because that means that for the case of the U1 gauge field, the partition function separates into two contributions, the part that is just the path integral over the gauge field and the gauge fixing condition, and the part that is just the path integral over the ghosts. To be explicit, the part CA is the path integral over the gauge field A times this piece here, and the ghost is the path integral of V minus the ghost action that we just had on the previous slide. As before, we want to solve this path integral by doing a Fourier transform of the gauge fields. So we trade A of X to the Fourier components A twiddle of, this should be K of X, A twiddle of K. And we want to recall that we have introduced the gauge field in order to make scalar QED invariant under local gauge transformations. So these were phi going to e to the I alpha phi and A going to A minus the derivative of the function alpha. Since the gauge field or the meta field phi was periodic in imaginary time, this means that also the function alpha has to be periodic in time. And that in itself means that the gauge field A has to be obeying the same periodic boundary conditions in imaginary time. The gauge fields have to be periodic, so that means that the Matsubara frequencies K that we have in this expression up here must also be the bosonic Matsubara frequencies 2 pi and T. Plugging in the explicit form of the Fourier transformed gauge fields, we find that the gauge part of the partition function is now given as the path integral over the gauge fields A times e to the minus 1 over 2 beta V times the sum over all k's, and then the action is quadratic. It contains the term that is just coming from FAB, and it contains the term that is coming from the gauge fixing condition, the Landau gauge fixing condition, which gives us an additional term that's 1 over Xi times KAB, KA, KB. Because it's quadratic in the action, this path integral is Gaussian, so we can perform the path integral explicitly, it will give us a product over all case. So this becomes this, the sum in the exponential becomes a product of the exponential, and each exponential will just give us the determinant to the power of -1/2 of the matrix that's in the exponent. And this is just this matrix that we had in the expression given in equation 36.9. So in order to further simplify this expression, we would have to calculate the determinant of this matrix MAB. To do that, we can decompose the matrix using two projectors. So we have the projector PT, which is delta AB minus KA KB over K squared, and PL, which is KA KB over K squared. These projectors fulfill the usual projection rules. It means that the contraction of PT times PL is 0, PT times PT gives back PT, and PL times PL gives back PL. In terms of these projectors, we can write down the matrix MAB as K squared times projector PT plus K squared over Xi times projector PL. This means that the eigenvalues of the matrix with respect to these particular projectors are K squared and K squared over Xi. We can look at the multiplicity of these eigenvalues by calculating the traces of these projectors. Calculating the trace of the projector PT is delta AA minus 1. Since we're in 4 dimensions, delta AA is the trace of the unit matrix in 4 dimensions. That's 4, minus 1 is 3. And the trace of PL is just 1. So we find that the matrix MAB has eigenvalue K squared with multiplicity 3, and eigenvalue K squared over Xi with multiplicity 1. This gives that the determinant of the matrix is just the product of its eigenvalues, so it's equal to K squared to the power 3 times K squared over Xi to the power 1. As a consequence, we find that the partition function ZA is given as the exponent of -1/2 sum over all k's logarithm of K squared to the 4th power plus 1/2 sum of all k's logarithm of the parameter Xi. For the ghost part of the action, the Fourier transform can be implemented in the same way as with the gauge fields. We find that the ghost partition function is given as a path integral over the ghost fields C bar and C, e to the minus 1 over beta v, sum over C bar K squared C. We can write this in terms of the determinant of this operator K squared, that's just K squared itself, and we have that the ghost partition function is the product of all K times K squared, which is the same as e to the sum over all K times the logarithm of K squared. Combining all parts, we find that the total partition function for U1 gauge theory is given as the product of CA times C ghost, and that's the exponent of the expression for the gauge field partition function and the ghost partition function. In the large volume limit, the sums just become sums over the Matsubara frequencies and the integral over the wave numbers K. We find that the integral over constant in dimensional regularization vanishes because it's no logarithmic divergence. And as a consequence, we find that the term that is the sum over the logarithm of the arbitrary gauge parameter Xi just goes to 0 in dimensional regularization. Of the remaining parts, we now have that the partition function is given as e to the -1/2 sum over K logarithm of K squared to the 4th power, and the ghost contribution plus sum over K logarithm of K squared. One clearly sees that the ghost and the gauge field parts have the same form, but the ghosts come in with a minus sign and a factor 2 with respect to the gauge fields. So if we take into account this contribution, we find that the partition function is e to the minus 1/2 sum of all k logarithm of k squared to the second power. We can write this in terms of the Matsubara frequencies omega n and the spatial wave numbers k squared in the following form. And if we compare this result to, for instance, the result we had in equation 33.14, we find that this partition function is exactly equal to the partition function of two free real massless scalar fields. So we find for the pressure of a U1 gauge field that it is equal to twice the free pressure of a massless scalar field at temperature T. So we have that the pressure of the U1 gauge field is twice that, twice pi squared T4 over 90. This result for the pressure is nothing else but the pressure of perfect blackbody radiation. And we note that of the original 4 degrees of freedom for the gauge field A, which is a vector field in 4 dimensions, so it has 4 components, the 4 components were the power of the k-squared term that we had in the piece that was given in the CA, but the ghost canceled 2 of these degrees of freedom, so that we ended up with just the 2 physical degrees of freedom for the U1 gauge field in 4 dimensions. This concludes the present lecture.